Any questions so far? Any questions that I would like to you would like to ask me before we move further ahead? Any of you? Are we okay?
Yes, sir.
Perfect. So, see, I generally upload my slides beforehand. This is giving you an opportunity for you to, of course, browse through and come not prepared. I would say just get familiarized with what we are going to do. Up to you, whatever strategy you wanted to do. But I generally do that. And if you have any issues, I would like you to discuss because your doubt could be a general doubt for others also. So, of course, there is some limitation regarding the class size, but I would like to have a more interactive session rather than I speak as a monologue throughout for an hour. Okay, so anytime, any point, if you need, would you like to interrupt me, I would be happy to invite that. And anytime, if you would like to ask the questions, let's have that so that we will elicit some discussion. Okay, so let me share my screen. Hope you guys are seeing my screen. Okay, so we are trying to see how process control problems are technically different from a design problem, which is that we have learned mostly. So how this is slightly different in the context. So we were trying to look at an example. Of course, the simplest example one could think of is a mixer. And mixer, how there are two streams getting mixed. Then you have an outlet stream going on, and you would like to have a fixed or like a desired specification for the outline. A typical problem that you would encounter in any process industry, be it you're an entrepreneur, be you're an engineer or whatever, or consultant, wherever. Okay, in the design, so what is the design? So design, why? Because see, these are all design is a disjoint activity. Somebody who would design would not be fixing the controls on it. So the designer's perspective would be, okay, this is the tank size, this is the volume, this is the RPM of the impeller, this is the power rating of the motor, so on and so forth. So at that time, what he would like to see under maximum, so see, they would assume a nominal condition. So nominal conditions this is what I highlighted that word nominal. Nominal is that conditions are those conditions where you expected to operate uh, most of the time. Anything from nominal is an anomaly, technically speaking. But most of the time, you would like to uh, operate under nominal characteristics. So you design a system or design a process, design a plan. So, for instance, when you drive a car, most of the time your nominal speed of driving would be possibly between, if it is a city, it may be between 40 to 60, and maybe in highways between 80 to 100 expected. So you would see that the performance of the vehicle or the car would be maximum under these specified ranges. Okay, because that is what you would set in. Otherwise, it's not very easy for someone to do anything. Like because if you would like to have a wider operating condition, because the speed of the car could be ranging anywhere between 0 to maybe 180 to 20, whatever. So you cannot guarantee the performance in all the regime. In fact, it's not recommended also. Why do you need to waste a lot of money? So you would expect that, so you would see that fuel efficient range most likely between 40 to 60 when you drive it in a gears like 4, 5 or 6 and maybe between 80 to 100, something like that. So this is the designer's duty. So I think they would do a good job. But the problem is like this. Okay, so you design a vehicle and you are expected to drive at 60 degree, sorry, 60 kilometer per hour, and assume. So that is under what you call uh, non-anomalous condition. Let's say there is a rain that is falling. So you would not like to drive fast. Why? Because there are issues of skidding, sliding. You might not be able to stop the vehicle even if you apply brakes, so on and so forth. So this is like a disturbance that you would see. So you cannot accommodate for 100% disturbance, but you could be able to do some extent. Okay, so what I am trying to say here is the design problem is mostly assuming things are under steady state condition. So if things are not under steady state or nominal, I would like to, so nominal and steady state, I would like to use interchangeably, but mostly nominal. Okay, but if there is a uncertainty, so in this particular operation, you are assuming that under nominal condition, okay, x2, of course, x2 is the pure speed that as expected, you see that with a flow rate of W2, okay, x1 is a mixed speed, okay, in which W1 is a mixed field in which the mole fraction of A is x1. Fine. Then you are going to have the following condition. Let's say if the conditions got changed. So if so, you are all under. So the previous design is all under the assumption that x1 has a constant composition. Sorry, W1 has a constant composition of A, which is x bar 1 under nominal condition. Let's say you are unable to retain that, huh? So then your x1 would will be varying it. So see your W2, which is to be kept beside to make x as xxb, you wanted to make x as xxb. Our decomposition is equal to xs is some constant value. Then you see that W bar 1, okay, the function of W bar 1, which is the nominal operating flow rate, and also this X bar 1. But now what is happening? This X bar 1 is not really an X bar 1. It's like an X bar 1 of t, which is varying with respect to time. So you see that your W2 would also need to vary to make the X2 to be compensated. So, but let's say you don't have any measurement of X bar 1 t, what will you do? So you don't know if it's varying or what. You only have the access of your outlet composition because that is the final specification. You check it, okay, so there is some variability. Where is this coming? Because if you don't have, if you are not placing a sensor on X1 to see that what is the variability or what is the time, the value, what will you do? So that's a problem. So there are three ways by common sense, there are two, three ways you can mitigate. So let's say you don't have any, so let's say so you are a plant in charge, okay? You figured out that this X, which is the outlet composition, is varying with respect to time. Because any product that is being sent to out of manufacturing facility, somebody will have to do a quality check. That quality check, there is a lot of variability. So then you as a in charge, be an entrepreneur, be an engineer, decided to do a check. You kept a sensor here and measure what is the value of uh, x1, sorry x. So you are seeing that there is considerable amount of variability in x. So how will you be able to kind of control that? Because that is not what you need when you want to sell your product. So one option, as I told here, is you measure X and correct W2 because you have a
Hello, sir.
control valve. Go ahead.
Sir, your voice is not very clear. Like we have to make a lot of efforts to understand what you are saying.
Yes,
What
sir.
about now? Is it any better?
Yes, sir, it is better now.
Hold on. So let me also switch off my fan to avoid any disturbance. So it should be better now.
Yes, sir, it's perfect.
Yeah. So can someone give a yeah? So the point that I was trying to say here is this. So how you are you as an engineer would play around with these situations. So you have decided to invest on keeping a sensor here. Okay. So my product quality is more important. I cannot waste it. There is no harm in putting a sensor. I am ready to pay for that. You sense the value by putting a sensor. So then what you could do? Okay, so if you know the sensor measurement, it is varying. You can of course control your W2 value to make that your outlet X has desired value. So see, your equation says so anytime you can isolate W2, W1 to calculate what is the corresponding value of XST. Or by natural thought, you can also, okay, I can control this pure feed to achieve the desired composition as I require. So this is one way to do it. Okay, so then there are, so but your what you call uh, but let's say your finance team told sir that this sensor is not cost effective. You have to invest, let's say, lakhs of rupees to purchase this sensor. Okay, but then you ask, what will you do now? So, okay, so then they did a market survey and came up with this. Okay, so sir, if you keep a sensor here, that sensor is seems to be a bit more cheaper. The sensor you can keep in the upstream is cheaper compared to a sensor you can keep in the downstream. Okay, because then you will have, since you cannot kind of waste a lot of money, so you keep a sensor here. Then what is going to, so you know the inlet variability. So this is inlet. Now you will be able to still very understand the variability of inlet, and you can do a control on your pure feed. This is another option. Okay, then uh, look, this is a bit cost effective option. Then let's say now you are working with selling drugs with 99.9 purity, and you are going to get lot of profit on this. But if there is a 1.01 percentage variability in the product, your overall product would be rejected. So then what you can also do, you don't worry about investing now, because your product would give you enough profit, and the quality of the product is so stringent, otherwise you will not be able to sell it. So you may be also decided to keep two sensors, one on the outlet, one on the inlet. Again, use those information to play around your pure feed to get the outlet composition. Fine. So these three characteristics is what I have mentioned. So this is particularly the case one is what I told. We keep it in the outlet. And case 2 is what when you keep a sensor in the inlet, and case 3 is what you don't worry about bleeding your funds at the moment, but because you are sure that your product would give you enough profit. It's a very specialty chemical, and when you send to the market, it's going to give you, and you may be probably one of the very few players in the market, so that when you send things out, you're sure that people would buy it. Then, of course, the large is a naive way of doing it, using a larger tank. In the sense that what would happen if you use a large tank? You have a very large tank. Uh, generally, and if you work with high volumes of data, so because then the variability will not be manifested. So due to large capacity, but then you have to invest a lot on the what you call capex, capital cost. Why? Most of the time, all the specialty chemicals or specialty products, you don't need to make it in bulk. For instance, it's a pharmaceutical ingredient. You won't produce it like petroleum products because because you the way you would like to inject in a drug, it may be mgs. You would see the drug. So most of the active pharmaceutical ingredient may be 1 mg, 2 mg. So if you see, maybe sometimes it could be 500 mg. 500 mg is also too less, you see. That may be what you see in paracetamol or even drugs like antibiotics. It may be 500 mg maximum. The rest all are like coatings, other bulk materials, so on and so forth. So there is no point in making this product too much and store it because most of them will have a very short shelf life. So whenever there is a market demand, you make it. When you get an order, you make it and sell it. That's all. Because it's not like you make it. Okay, I'll keep it in 1 month, 1 year in my shelf. So because these are all stringent quality, has this all had to go for stringent quality checks. Maybe if it is made, let's say 2 months or maybe 1 year older, your product may get rejected. So the third, of course, is not a wise way of doing it. So now let's look at A, B, and C, or in fact, let's look at A and B. C is a combination of A and B. So what is that I was trying to say here? So you would measure a composition and you would go AT. So you see this word AT, we might see it repeatedly. AT means analyzer and transmitter. So why do you need to analyze and transmit? So analyze, of course, that would give you the information regarding the composition. And you see, you have to control something. See, control valve sitting over here is not on the output line. It is on a feed line. So you have to pass this information. So you are keeping the sensor, let's say here. You will have to pass this information all the way right here. And there is a controller. So we'll talk about controller, because that is one of the key aspects that we would like to learn. And it is written as AC, which is analyzer, controller, whatsoever. So basically what I'm trying to say, there are two things which is sitting over here. So two hardware, in fact, three hardware, you see. This is a hardware, and valve, controller, another hardware, sensor, another hardware. So now it's important that each three of them would communicate each other. How do you communicate? So these are, so let's say your sensor is giving. So how a sensor works basically? You might have seen many various sensors, right? For instance, thermocouple, so on and so forth. So how the general way of the general operational principle of a sensor is it would have a sensing element. Okay, so let's say this is a sensor. It would have a sensing element. It would be inserted to somewhere where you need to sense. Okay, so this probably in contact or maybe would have a envelope or something like that. And sensor would give, most of the sensors are generally giving a signal output. So let's say your temperature is, for instance, thermocouple. Thermocouple will give you some voltage change or a current change happening when you touch, when you place it in a particular environment. So you are basic. So when you use them to measure something, you are not getting that value actually. It would give you a signal which is proportional to the actual value. So let's say your actual value is 50 degrees C, the signal may be some let's say 3 volt or something like that. That is what, because they are all electrical equipments, you see. So what would eventually happen? So you will have to play around with the signals now, because otherwise, how do you pass this information from one unit to another? So then you probably will have to do a hard wiring. So these are all electrical signals. So you probably need to do a wiring. So now there are in the market there are something known as smart sensors. So these are all conventional sensors, and you will also hear a word called smart sensors. Smart sensors are generally, so it's like Wi-Fi. You don't need a wired connection. They would both communicate in a wireless fashion. But still, you will have to communicate. Okay. So most of the time, but see, again, you would have to work for your market. Smart sensors are expensive. If it is needed, you can use it. But if your application doesn't warrant a smart sensor, why do you need to go back and purchase it? It's not worth. So then it's an electrical signal that connects all of these. So you probably need to do a wiring. Okay, then controller would do some calculation. What is the simple calculation that you can do? Okay, let's say if there is a nominal value of W, you probably do some correction, because this is the required value and this is the current value. Okay, and do some correction. Kc is some correction factor. So it can be positive or negative, but you can always calibrate. So based on your inlet and output, you do some correction to make the W as desired to keep access equal to access speed. So such control mechanism in principles are called feedback control. Why it is feedback? You are measuring something. This information is fed back. So there is a loop which is working in a feedback fashion. So what is the problem here? Of course, not a big problem though. You can only act after something happened. So you have to understand that there is something bad happened. So you go back and correct. Of course, this correction would be faster because electrical signals are faster. So it would be an instantaneous correction, but the problem is the correction would happen only after something has occurred. Any questions here? Any questions at the moment?
Um, yes, so you mentioned that one of the sensors would be more cost effective than the other one. So would you please explain that again?
Okay. For instance, so none of the sensors would be of the same cost, right? Would you agree that? Let's say your inlet is a more sophisticated. So let's say this is a mixed field with A and B. So it contains two variables. So if you need to isolate one and what you call calculate the purity of the other one, let's say you need a composition sensor, and there are two. So then it might require you need to do a spectroscopy and so on and so forth. Who knows? Okay, then such instruments in general are very expensive. But here, if you see, you are only worrying about one output, one variable. So there is not A plus B here. So you can still get away with a sensor that isolate one and measure one, because you have only one variable's composition to measure. So they tend to be slightly cheaper compared to the other one, or the other way around, whatever. So what I am trying to say is sensors are not, so their cost would vary depending upon the variable that you need to measure, the place that you need to insert. For instance, if you are inserting a sensor more corrosive environment, you should have that much level of packing and so on and so forth, so that it would survive that condition. So sensors would generally be, his expenses would vary depending upon the application, type of usage, and the level of accuracy that you need. So is that answers you?
Right, sir.
So any other question?
Yes, sir, got it.
Yeah, thank you. Any other questions? Okay, I'll go ahead. So now look at this case. This is what measuring beforehand. So you are now looking at a variability in the incoming feed. Huh? So you are now doing a prophecy. So okay, so there is some variability here. Okay, before it affects my system, let me go and try changing the output so that when this effect comes in here, this effect also comes in here. So that you are more what you call proactive, but this is, let me use this word, this is more reactive, right? Something happen, you go and do a correction. This is proactive. Then what? But what is the problem of this proactiveness? So I don't know. So let's say you measure this, okay? If you don't really know if this, how the variability in X affects your final product X, that's a danger. But what, when we do this, you are actually looking at the final product and do a fine tuning. Now you anticipate, or rather you measure and do some anticipatory action. If your action, even though it is more proactive, if it fails, your action is incorrect. If you have an incorrect action, the whole product is now going to get wasted. So you expect that there is a change. Let's say your sensor somehow has given a wrong reading. It should give you, it should have given you 0.5, but let's say due to some malfunction of this, you got 0.9. So then what you will have to do, your reaction is you are now proactively correcting. Okay, this is now 0.9. So there is a large change I need to nullify by increasing or decreasing the flow here. Then you suddenly changed it very drastically, but it was a sensor measurement mistake. It is possible because they are electronic equipment. There is a very likelihood. Most of the problems in industry mostly related to the instrumentation incorrectness. So then you pumped in, you did a large corrective action, fine. But after the 0.9 for 2-3 minutes, maybe seconds, it came back to again 0.5, which means that this was a wrong reading. But by that time itself, you have done some large corrective action. Fine. Then what would happen? Your whole product is now waste because you have unnecessarily pumped in lot of unnecessarily pumped in the correct, what you call W2, which should have corrected the anomaly, but actually there was not an anomaly. So feed forward control, even though it is good, it's a double-edged sword. So unless you are very, very sure about it, you apply, because it would tend to accentuate your downstream process effect. Any doubts here? So this, okay, so now this is generally called feed forward. So you recall the keywords. The previous one was feedback because you were trying to correct, but this is feed forward. So you are proactive. So, but the problem, as I mentioned, if you are if you miss your target, okay, if you miss your target, for instance, let's say you see football game, fine, penalty shootout, typical example. So the goalkeeper don't have you, he or she, of course, he most of the time, he would be in a position to, he is just judging based on somebody hit the ball, based on his, whether he runs, or whenever the kick, whenever the player kicks a penalty, he would possibly looking at the direction. Sometimes people would very nicely fool the goalkeeper. His with footsteps and the kick would be indicating that he would be hitting it in one direction, but he would have done it in the other way direction. So most of the time when you jump it to catch the ball, it may go in the other side. It would eventually hit in a goal instead of a save. So the same problem here, you are anticipating and doing something, but your anticipatory action is incorrect, go on. So then the entire thing is waste. Fine. Any doubts so far? Is this clear to all of you? Any doubts so far?
Yes, it's clear.
Perfect. Okay, so now the third is what you call it's what you call as redundant approach. I'll use that word again, redundancy. So redundancy means what? So now you have an information that is coming from here, you have an information that coming from here. So now you smartly integrate it. So for instance, if you give it a larger hint that it is changing in direction, and if you get some information that there is not much change, you can do a suitable combination of this information together. So basically, it would look into two. So it is a feed forward and feedback combination. Yes, best, because then you are doubly safe, right? Like it's like having an airbag and a seat belt together. But of course, you will have to buy a vehicle having maybe 6 airbags, which is more costlier. So let's say if you're sitting inside in the rear seat of a vehicle, you would have both, and it's like having a seat belt. You put a seat belt, and also there is an airbag kind of a thing. So what you would have to pay, generally all the vehicles will have only front airbag. So now you need to have it in rear also. So you should be ready to invest more. So of course, safer, best, but yeah, so it would bleed your finance. So the large one, as I told, because it's a larger tank. So larger tank, it's like this, okay. So you don't. So let's say if you might have seen the water tank, right? So water tank, if the volume of the water tank is less, you would see that there is more oscillation happening. And let's say you are talking about a huge level water tank, you don't see that if, you don't see too much of oscillation. Why? Because it's enhanced capacity. So generally oscillation tends to damp out due to the capacity. So similarly, if it's a large tank and there is a small change, it would eventually not visible. So, but again, you will have to have an increased capital cost, which you don't need. So eventually, when you work in an industry, so you have to do this when you design an industry or when you give a consultancy advice, you'll have to take care of all these factors. So now what, so see, eventually what we did, so we have now, so let's recapitulate. So what we have seen, so nominal operation is basically a design spec. But when you work in reality, things are unsteady state. When things are in unsteady state, you need to have a guard, right? So that is basically your controller. And there are multiple types of controllers. You have seen feed forward and feedback, feed forward and feedback controller. So now the question is this. So let's say if you look at in feed forward and feedback, there is a relation that helps you to correct something. No? Here also there is a relation that helps you to correct something. Now, how do you know this? So for which you need to know the overall dynamics. This is a simple dynamic. So you do something. But if you really need to make an accurate decision, you need to model the whole thing. Because you need to know how W2 affects your X, so on and so forth. So even though it's a simple example, this also motivates you to need to have a modeling exercise. What modeling? Dynamic modeling. because you see everywhere we need to put a T. Because of this T, which is varying with respect to time, you also need to know how your system is also varying with respect to time. So then, so yeah, so basically what I'm trying to say is this is what we would learn in maybe in another 2.5 months. We would learn how to characterize an unsteady state, how to design a controller, how to, again, so there is also some parameter, how do you fix this? So let's say there is some Kc coming in. So your output is a function of Kc. So you will have to keep this Kc fixed or rather tuned so that you would get your best performance. So it is also known as tuning, controller tuning. So so what I am trying to say is these were, so of course this is an example, and we are not, and we have done as a qualitative analysis. So in the coming lectures, we will try to see and understand each of them in a more quantitative fashion, because eventually you are playing with numbers, because everything is a number game. Your purity is a number, your cost is a number. So qualitative analysis won't work. So okay, open up something, close up something. You will have to say what, how much you want to open up. Let's say 50%, 55.5%. You need to know that exactly to make the accurate decision. So this is what we would follow later. So just to say, so maybe this is maybe too early an introduction. So what I am trying to say is, so if you see how a feedback control works, okay, there is a controller right here, and you have seen a control valve and your tank, correct? And the tank, there is a sensor that gives you this information and doing a feedback. Don't worry about what I would say, what is this XHP, what is this milliamperes, and so on and so forth. Milliampere, you should understand that most of the signals are electrical in nature. So milliamps measure the value of that. So another interesting thing here is, you see the controller always talk in terms of milliamperes, voltage, and things like that. But your final output, when you talk about the market, it has to be in your quantitative fashion, abstraction. So there should be a conversion, what you call suitable conversions from what you call electro. Basically, there are three things. So process variables. So that would have its own units. If it is a concentration, it would have its unit. Let's say it is a temperature, it would have its unit. But within the control system, it mostly operated by signals, right? So control system would have and sense. So I will say control and sensing system, because you cannot separate them. So they would be mostly dealing with in signals. You see, you now see how CS and so you electrical engineering and all coming in here. If it is a signal, I don't know, you have heard of a word called signal conditioning. Okay, then have you heard of a word called filtering? So, but all of these would have to adequately apply here at the necessary need. So, this is a very strong. So, here is what we need to learn a deep dive into this kind of area. Signaling is basically, you have to talk about signal conditioning, you'll have to know about the signal properties, and you'll have to know about so many signal characteristics. So it's going in the other side. So again, so what I'm trying to say is this: every control system would have two or three. So most of the time, your input and output would be in physical variables, while inside whatever loop we see, it would be mostly in terms of signals. It can also be pneumatic signal, okay? Pneumatic signal. It need not be always an electrical signal. It could be pneumatic, which means air. Air is also used to signal because pressure waves you can send. pressure wave would also give you an indication about a change, right? So pressure wave is also it's like also instantaneous. If there is a change in a line, pressure change in a line, immediately it would be sent in the other. So either it could be through an electrical signal, and there are some specific cases where you use pneumatic signal. We'll talk about that. Okay, so now we have seen about a physical plant. This is not only related to physical plant. Have you? I don't know whether you have heard about automatic glucometers. In India, it is of course not common, but of course in the US, these are now picking up. So let's say you are having extreme case of diabetic. So previously, what people used to do is either you take a tab or you measure before any meal you take. You generally measure the glucose level. Of course, what you will have this home kits for glucose available to measure. Then based on your level of glucose, you will have to inject an insulin. Okay. And based on that, how many units you would need to inject to kind of reduce the excess sugar that would generate based on the food that you take. So this is people also seeing it as a control problem now, wherein it's like pacemaker kind of an equipment. There is something that you would inject in subcutaneous layer, and that would give you your glucose level continuously. Fine. And if there is a drastic change in the blood glucose, fine, it would automatically inject insulin. So what it should have a sensor. Sensor is basically your the used to measure the glucose level. Fine. And there's a what you know as a glucose pump, which used to it's like an injection, glucose injector. You will figure out you have a control mechanism. Of course, this is a feed forward control or feedback. This is a feedback control. You see the measure. You measure the glucose, and based on the measure, you have this what you call automated mechanism that helps you to inject the desired value of glucose. So any questions here? I'm saying, so I have put this figure, whatever we are learning, it has application beyond our domain. Again, driverless cars. Again, aerospace application. Autonomous navigation. Everything. So the broad perspective, the learning elements, what you are learning, you are taking, you are having, is very generic. But we are focusing on process planning. That's all. But the material or the theory or the methods that you are learning is applicable to anywhere you would need to have a automated system of operation. Any questions so far?
Hello, sir.
Go ahead.
So do we really need to have sensors at the output end because any changes in the final values will be only because of the changes in the initial state. So if we can control them, then there is no need of having sensors at the output end.
So you are right. So that is what we have learned in feed forward kind of a strategy, no? So you measure in the input and do a control, correct? That's what you are trying to say, right?
Yes, sir.
But as I told, it's a double-edged sword, no? If your anything happen means that actually had a happen. But if there is a change, if there is some level of miscommunication happen, and when you go back and do an anticipatory correction, and if there is some issue happen, it would be a haywire. Got it?
Sir, that is possible for the first case as well. There can be errors while calculating the final values.
No, there are two things, right? So one, you should know. So the changes, hold on. So here, what you need to know how this changes is going to affect your output. Because your control action is an anticipatory control action, correct? So let's say delta change here. You should know how that affects here. Fine? Are you getting that point?
Yes, sir.
Because your product is not X1, it's a mix of W1 and W2. So you should be able to calibrate, foresee what a delta 1 is translating to, whether this delta 1 is exactly delta 1 or a function of delta 1. Sometimes this calibration, so change in here may be magnified, or maybe it would have a linear relation, or you may have a very different relation. Are you getting this point?
Yes, sir.
So if you can exactly map this relation, that's okay. But if you are unable to map, so if let's say if delta in one is, you have incorrectly mapped how your x is varying, and you have incorrectly mapped this delta 1's effect in x1, then whatever change you are doing is making things worse. While here you are doing the changes on the actual variable. Are you getting my point?
Yes, sir.
So it's like this, right? Uh, so there is some level of prediction needed here, because you have to see what is happening, what is the change in the delta 1 in the input is in the output. So if you could develop that relation accurately, let's say most of the system, as you would really see in process industry, are very, very nonlinear. So if you can do it, perfect. But this is a safer way of doing it, because you have seen what is happening, then you are doing a correction. Fine. This is like a belief, like you have seen and doing a correction. While, so I will say, it's like this, right? So one is, let's say you use a meteorological information. Let's say, so let's say so of course it's a very, what you call, it may not be a convincing example. So let's say your meteorological data give you an information that today 10 a.m. there would be rain, correct? So what you have done, the without looking at whether rain happening or what, you have opened your umbrellas at 10 o'clock. So if your predictions are good, fine. Then there is a point in opening your umbrella. While when you do it in reactive fashion, whenever there is a rainfall, so you open it up. So you might wet little bit, but you would quickly open it up. But in the other case, you based on a prediction, but let's say if your predictions are exact, if there is a rain falls at 10 o'clock, then there is no point. But otherwise, you would have done opening an umbrella without the need of it, no? So if you understand what I'm trying to say.
Yes, sir.
Both of these methods have their own advantages and disadvantages. So I'm not advocating yes or no. So it's up to us to judiciously, in cases where we can map this relation exactly, there's no harm in putting a feed-forward control. So if you are unable to map, you can do, or if you can do both, absolutely fine. Both you can do. So it's up to you, based on the field, based on the scenarios, what take you need to do. Hope you understood it. Okay, so what I am trying to say is, so in process industry, like any other, maybe in aeronautical or even many other applications, would have many levels of control. Because eventually you cannot collapse your system. It has to be against collapse. It has to work So there may be very, very different layer. One is in process industry, especially, you would need to forecast the market demand, how much you would need to produce for next 5 months. Then you will have to start purchasing the raw material. Then you have to do what is known as real-time optimization and constraint control, which means that how in what is the operating condition that you need to fix for 1 day, 2 day, and whatever we are learning is in one more layer below, which is known as regulatory control, which is directly talking it with the plant. So there are upper layers which in every control system, one would be a longer horizon. You would have to plan what is happening, whether, for instance, so many of the, I don't know whether you have seen it, like many of the garment making companies, for instance, Vans, Fusion, Allen Solly, so on and so forth, they had to change your strategy to making masks during the COVID time, you see, because their apparel is, of course, not getting sold off. Okay, but then to keep the brand active, and they started making masks. So I'm saying, so this planning, so this is so you cannot plan that, no? So nobody was trying to plan there would be a COVID time. Otherwise, they would have made a lot of their own garments, but it doesn't work. So there was a problem in the planning. But then they had to do a course correction. It was a feedback control kind of a thing. So what I'm trying to say is you need, so it's the same in here. So you would have to plan in a process industry. You have to buy raw materials, then you have to see how you are going to operate in this day, that day. But whatever we are speaking, this real-time correction is not, so you see the time scale. One is in the days and months, others in hours and days, maybe in minutes and hours. And the other one, what we are speaking, is in seconds, whatever we are going to do. So the top layers is essentially fall in the domain of what is known as scheduling and advanced process control. Professor Ramteki, I think, is taking advanced process control. I don't know. So currently, I think nobody is teaching scheduling in our department, but so they are interconnected. Scheduling should talk to advanced process control layer, and advanced process control will give high-level information to the regulatory layer, which is what we are going to learn. Then, of course, there are safety and things like that. So whatever we are learning is basically one of the lowermost layers of control. And when you do advanced studies, you would talk about scheduling and advanced process control on the top and the top. I just gave you gave you a hint. So what is that eventually we need? Okay. So this is what I told. So your output product should be as clean as possible, 99.9% correct, and it should not have variability. You one day you are keeping 98%, one day 99%. No, you should possibly your operating range may be just between 99.5% purity to 99.9% purity. So if you don't have a control, you tend to operate in a larger variability, but if you place a control on the top, it should have a lesser variability, because always the lesser variable output would have more market demand. Otherwise, what you would say, your production quality is not good. You have not tightened anything. People say that your production is fluke. Sometimes it is giving something, sometimes it is giving something else. All the FDA, all the market regulations for would have tight control on the output purity or output variable, whatever output specification. And eventually, what would happen is the quality. See, if you don't have a control, you see the output quality distribution, which this is coming from what is known as statistical process control. I don't know you have learned it. Statistical process control. You may also heard about Lean Six Sigma. You see, all are related. It's important that you make the connection so that you would understand the applicability. What is Lean Sigma? Sigma says you need to have as lean operation as possible. If you don't put enough control, you see the Gaussian curve of the operation would be as flat and wide, but if you have control, it would become more sharp and clean. Okay, so I am not going to go through this. So what it just says is that it's a development of a control system. Development is not a simple task. You need to identify the objectives, develop a model, devise a control strategy. You need to have hardware, then you need to install, then do a setting. Why we want to do it? Because it's a cross intersection area, right? So there is some hardware comes in, so you need to know a little bit about hardware. You need to know a little bit of mathematical modeling. You need to know process control, so on and so forth. There is something simulation. So basically, all of this would come in hand when you work real time in as a process control operator or a process control researcher or an engineer in the plant. With this, I would like to stop. So today we won't have any doubt clearing session, I hope, because we have just started. Next time onwards we'll have. And regarding the tutorial Monday, let me discuss with the TA and let you know. And if you have any doubt at the moment, we can discuss it at the moment. Otherwise, we can close the session for today. Anyone, please? Ashutosh?
Yes, sir.
Any questions?
No, sir.
Otherwise, shall we close the session then? So we don't have the doctoring slash this week. And regarding the tutorials, I'll let you know by email or WhatsApp whatsoever, so that you can communicate into the okay. You and Jay.
Sir, are we going to have the doubt session today?
If needed, do you need to have it? You tell.
No, sir, I don't think so.
Yes,
Yeah,
sir.
that's what sir was
We
suggesting.
haven't covered that much to be discussed.
Perfect. Next week onwards, we can activate that. Okay.
Yes.
Okay. Thank you, sir.
Okay, guys. Bye.
Thank you, sir.